Hello everyone, today I am going to deliver a lecture on analysis of section of flexure. Analysis, that means we will find the stress, strain, force, that if we design the section, then we will find the member section and reinforcement. Okay, let's see. First of all, I will see the introduction and sign convention, then we will see the stress in concrete due to prestress. Okay, and then we will see the math example of stress of concrete of steel immediate and after transformation due to prestress only. Pre-tension member and concrete eccentrically prestressed by exact and approximate method. And then we will see the math example of stress due to immediate and transformation due to and after transformation due to prestress only. Pre-tension member and eccentrically prestressed. So these are the concentrically and these are the eccentrically by exact and approximate method. And then math example of a stress of concrete immediately transferred due to free stress only. Post-tension member and eccentrically prestressed by exact and approximate method. Then we can see the stress in concrete due to load. It will be load, and it was due to pre-stress. It was due to pre-stress. And then math example of the stress in steel mid-span post-tension member and concentrically prestressed. And math example of extreme fiber stress mid-span post-tension member concentrically prestressed under initial and final condition. And then stress in steel due to load, which is a math example of a strain in steel mid-span post-tension member and concentrically. And cracking moment and ultimate moment and bonded tension moment, curvature analysis, bonded moment and composite section. So let's start from introducing sign convention. So here is the chapter. Before I'm starting, I'm just taking the sign. I'm just taking the reference of this book, Design of Prestressed Concrete Structure by T.Y. Lee. Okay, the sign convention we have been known by the analysis means of the determine. We can see here the positive sign for compression stress and negative sign for the negative for positive sign in compression and negative sign for tension. These are the sign convention. Okay, these are the index. Now we see the stress in concrete in free stress. So we have been seen here the stress in concrete due to free stress. So you can see here the stress in the force per area and stress we have been taking this formula. We've been seeing the before transformation and during the transformation and transformation of concrete free stress in pre-tension member we've been seeing here. So analysis section of flexure, you can see elastic theory up to 0.003 stress force per area. For concrete, we can see F equal to area of concrete plus NC equal to area of steel. So F initial equal to gross area into n minus 1 into AG. So Fi initial equal to Fi steel into As. As we know that this is the steel. So I will convert. So the steel will be n into As equal to concrete. So Ag equal to n into As transform section from the steel minus As. So Ag equal to As, if we common the As, then n minus As. So in this way we can put in this value. Okay. So let's see the math example of I'm just zooming. The math example of stress concrete and steel immediate after and after transfer due to free stress, pre-tension member and concentrically free stress by exact and approximate method. Okay. So let's see here. Here we can see the pre-tension member and the similar, so that shown in figure is below. The section is 200 and 300 millimeter and concentrically prestressed with 50 millimeter square and high tension steel wire and which is anchored and buckled with the unit stress 1035 MPa and assuming then n equal to is given 3 and compute the stress in concrete and steel immediately after transformation. We can see all the data is given, as is given, as in initial stress is given n into even. Now we'll calculate the exact and accurate method. As we know, stress equal to force per area, so Fi I will calculate. So if we go to the rearrange, then it will be force equal to stress into area and found this value. Now we'll calculate the stress in F equal to initial into Ag minus As to putting this value and found 8.6 MPa, and delta Fs and found putting this value and found this value. So it will be losses at delta Fs, that means the losses. So still stress in steel after transformation, it will be initial stress minus loss of steel, which is 983 MPa. So it is stored after the losing this is stress. So this value have been found accurate or exact method. Now we'll solving this value for by approximate method. The loss of free stress in steel due to elastic shortening of concrete in is estimated by so delta Fs equal to n into S. As we know, here delta Fs equal to n into initial stress equal to force per area. So this is by initial force into Ag, the total area, and found 53.8. So and the stress in steel after losses, so FAS, so initial loss minus loss of shortening, so it been from 913. So the initial we've been seen the by approximate method, we have been found 53.8. On the other hand, we have been found 51.8. So these are the very similar. And after the steel losses, we have been found 981, and we have been found here 983. So these are the very close to, these are the two value are very close. So I can recommend that we can use the approximate, we can avoid the approximate, and we can use the accurate and exact method. Okay, so stress in concrete, which is Fs equal to As into Fc into Ag, and found 8.5. So there is the some formula we've been seeing. The exact method we can use this formula, and approximate method we can use this formula. Okay, so this example in depth. Now we can see the math example of stress of concrete after immediate transformation due to prestress only. The pre-tension member eccentrically prestressed by exact and approximate method. So let's see. So you can see here the eccentrically load which is taken. This is the force, and this is the CGS, which is CG of concrete as found here. So we can see stress F divided by plus minus my by I. So which is m, we know m equal to force into perpendicular distance. That's why force into perpendicular distance, that means that means E. So this formula we will use. So let's see. As a post tension member is similar, so the shown figure is below. The section is 200 into 300 is it is the eccentric, and prestress is 502, prestress with 520 millimeter square highest steel in wire is encouraged due to Buckhold at unit stress 1035, and CGS is 100 above the bottom. So these are the given. So keep in mind that, and assume the n is given, and compute the stress in concrete immediate and after transformation due to prestress only. So we can see the figure is given. Now we'll use the exact method. So I will calculate the exact method. So we know the S equal to given 502. Fs equal to given, and n equal to given. For transformation section, we know n minus 1 into As, which is found. These are the value. And how will calculate the Ag plus n minus As into As, and putting this value and found in this value. Force equal to, we know, stress into distress, and putting value and found this value. And Yb, this is the from bottom Ay. So as we know, this is the section 1, this is the section 2. If we calculate here, A1, Y1, A2, A2, Y2 divided by A1 plus A2. So A1 we know the 200, and the Y1 we know the 300, and it will be and 150. And another one as we've been found here with 26 where this is the transformation section 2600. So we are finding here the 2600. I'm just changing color. Yeah, this is the 2600. So 2600 into 100, and in this way we found this value from bottom. If we calculate the top, then we can just deduct this value and from top. And how we calculate the E, as we've been found the bottom value of here. So bottom minus 100, then we will found the 48. As we've been seen here, thus all this value is given here. Okay. So 100 is given. How will calculate the 100? 100 is given, so there is no problem at all. So this 100 is given here. This 100 is also given here in the picture. So I equal to moment of inertia into d square, and putting this value and found this value. After all this value, and we just putting here, we know the stress equal to force per radian my by I, and m equal to force into perpendicular distance. Perpendicular distance, this is the value of E, which is we've been found 48. And putting all this value and found the top stress we've been found 0.6, which is close to 0, and bottom we've been found 16. All the values minus. And now we're solving the approximate method, and using this value, as we know the losses n into fc, and found this value, and stressing in steel initial minus final, and found 981. And after the lossing we will found f equal to this value, and now we will putting in this value and found at the top it is 0, and bottom which is 17. So these are the for eccentric method, then we can use exact method, then we can use this formula. For approximate method we can use this formula. Remember that by when using the approximate method, then we have been found the bottom is 17. On the other hand, when use the exact method, then we have been found at the bottom is 16.98. So these are the very close. Okay, so you can use as usual your desired. So these are the completed. So now we'll see the here another math examples of steel of concrete member, immediate transformation, post tension, and eccentric. These are the post tension. So remember that this is the post tension. Okay, let's read the question first. The post tension beam has midspan cross section is dark. These are the dark. There is no concrete, and the dark section is given 50 divided by 75, and thus wire is bigger shown figure. It is prestressed with 502 millimeter square of steel, and initial loss is given here. The immediate after the transformation of stress is reduced 5% owing to anchorage loss and elastic shortening of concrete. Compute the stress in concrete at the transformation. So it is the given. So using net concrete. So as we know, the force into stress into area, and found this value, and another force into stress into area have been found this value also. Net equal to net concrete of area, which is full minus duct. As we know that this is the duct will be deducted here, and for finding this value. And I will calculate the CG, which is YB A1 Y1 minus A2 Y2. What is A2 Y2? A2 means that this is the duct value, and found 553 from bottom. And how will calculate the top? And if we deduct this value and found top, I will calculate the E 155 as we've been found minus 75. 75. Then 75 is given here. As we know, the 75 is given here, the minimum thickness, and found 80. And the moment of inertia will calculating here, and all the data is after the finding all the data, then we just putting all the data here, and stress equal to force per area, and plus minus F minus U into Y divided by I. And for the top fiber we've been found 48, it's a positive 48 we've been seen here, and the bottom fiber we've been found minus 23. This is the minus 23. Okay, Now using approximate method, as usual we've been using f equal to s into fas and found a equal to this below. We will not reducing duct as we are taking the all the value, and y equal to 300 divided by 2. There is no deduction on duct as we've been in the total is 3, so take 300 divided by 2 equal to given 175 and I value is found. After finding this value and putting all these value here and finding this value as top fiber 4.2 and bottom fiber is 21. So by we can see the using approximate method, the top fiber is 4. Top fiber will be found 4.26. By exact method using net concrete method, at top fiber will be 4.83. But here we've been found 4.26. For approximate method we've been found bottom 21.30, but we are here we've been found by net concrete method, which is 23.9, which is very close, so there is no problem at all. Okay, so these are the inlet. Now we can see the stress in concrete due to load. So we can see how we calculate the maximum math example of stress induced in steel span in a post tension member and concentrically prestressed. So let's see here. This is the post tension and mid span at the span 12 meter of carries a superimport load is given here, and additional wing to wide is given here, and the initial prestress of steel is given at this MPa and reducing to 2 MPa. So this is the important, and often and the deduct all the losses assuming no balancing of the beam is given, and parabolic cable and has the area of given this value and is give this value. Compute the stress of steel at mid section. So these are the important mid section, assuming the all the bonded by grouting. Okay, because this is the lessons. So we can see these are the L is given and all the data is given here. Okay, this is the sulfate and this is the word, and these are the E value and the 170 and 600. Okay, so let's see. So given we've been seeing the stress is given here, initial and final stress 842 and is given as is given. So yield 6 is given divided by 175 as given. These are the sagging distance is found 175. That's why you dividing here, and eccentricity will be found there. So moment will be we've been found SL self-weight SL. What does mean is SL 12 is given here. So this will be 11 SL is given 11 we've been superimposed load. These are the SL which is 11. So WL square divided by 8, L is given 12 and found this value. M due to self weight WL square by 8 and self weight we been know the 4.4 is given here 4.4. The one weight or self weight is the same. And due to prestress F, so moment will be due to prestress. So you can see F equal to E as in the force into perpendicular distance, and F force equal to stress into area or area into stress, and founding this value. So after founding these three moment, we can just we just adding three moment as moment self weight, superimposed load self weight, and prestress. Remember the prestress moment will be deduct and found this value, and moment of inertia found, and F is found. After finding this value, just putting this all this value, then we'll finding the loss of stress, which is N into FC, and finding the net moment, and found 15.72 MPa. Okay, so let's see another the post tension. Okay, these are the inlet. So another math example of the we can see here the math example of extreme fiber stress at mid post tension member and concentrically prestressed under the initial and final condition. So let's see here the post tension bonded concrete beam is figure given is below, and the prestress of the prestress is given at the kilonewton, and initial steel is immediately after the prestress, which is eventually reduced this kilonewton due to losses, and the beam carries live load is given 45, and in addition to own weight, which is self weight is 4.5, and compute the extreme fiber strain is midpoint. Its condition 1 is under the initial condition with full stress and live load, and under the final condition after the loss of all have taken place in the full load. Okay, so you can see these are the given. For we know initial is given there, and the final is given for after jacking or elasting shortening. So y equal to, we know, d by divided by 2, and e is given d by divided by 2 175. How will get the 175? 175, these are the maximum set distance, or you can say the chord distance from the bottom, and moment of inertia and a, and how will calculate the moment, which is the W L square by 8, and how will calculate the W 4.5 only self weight. There is no other is taken, as we've been seen the 4.5 we've been in the only self weight. There is no live load is used here, so that's what the self weight moment is taken here. So after taking this, and we just using all this value here, putting all this value and finding that the top fiber will be for the initial condition. Okay, so initial condition, that means F not equal to F, no live load will be considered here, as we've been taking initial, and top fiber will be found minus 2.31, and for bottom is 15.93. These are the diagram. F for initial condition, F not equal to F, and no dead load is used. For final condition, we know the final after loss, dead load will be used on each. So you know the final will be used this forces, and y equal to as usual the same value, and e equal to as usual same, I equal to value same, a equal to same. The moment will be changed, as we know the 45 as these are the 45 kilonewton load we have been used as on weight. It is carried the live load that's given is here 4.5 is apart from the support. After founding, then 45 will be support taking. These are the now taking the shear force. It will be upward 45, then because there is no, then downward, there is no load, then downward, and there is no load, then will be upward. Okay, there will be 0. So in this way we calculate the maximum 45 into 4.5 is the distance, then we can find 202.5 Newton meter. This is the maximum moment. Okay, so moment live load 4.5 into 45, which is 20 joule. These are the moment. These are the we can found from bending moment, or you can use this hand calculation. And self weight we have been used 81 is previously. So moment will be total. So live load and self weight, and we have been used the total moment is 283 for final condition. So 283 we have been using. All the data is here, and found the top fiber is a minus 30 minus 87, and from bottom also minus is 1.1 is very close to. Okay, this math is in that. Now we can see stress in steel due to live due to load. Okay, these are the due to elastic shortening. We don't need, as we've been seen another lecture for elastic shortening eccentric. So we can use this here. Okay, let's see here. So analyze the section at the station pretension. So another example you can see here. The pretension concrete beam has initially is given here and shown figure below. The eccentrically pretension is here, and the anchor and the buckle hot and unit stress is given here, and CGS of the strand is above the bottom is fiber 100, and assuming n is 7, using the exact method, the elastic theory and approximate method, analyze the section obtaining stress concrete immediate and after transformation due to prestress. It will be this example. Okay, let's see. we can use this. The given data is here, and force equal to stress into area as into the transformation area as a gross area into steel minus n minus 1, and YB, which is the CG, A1 A2 Y2 divided by A1 plus A2, and found this value, and Y top equal to total minus this value, and found here. And eccentricity 245 is the total depth divided by 2 minus 100. How will calculate the 100 is given in the CGS of the between two steel, and moment of inertia is found at this value, and after putting found this value, putting all these values here. Just problem is finding the bar of Y bar of here, and after the top fiber is 0.3, which is close to 0, and bottom fiber minus 30.61. Okay, by approximate method we can use this here. So at the top fiber, which is 4.3, but in the top fiber was close to 0. On the bottom fiber have been found 17.25 minus 17.25 approximate, and it is 13. So all of the value are the close to, which is very close. Okay, now we can see these are the stress in steel due to load. Okay, due to load. Okay, ultimate moment. Okay, just we can go this book, stress in steel due to load. This is the stress in concrete due to load. Stress in steel due to load. Okay, steel. Okay, stress in steel due to load. We can see here the variation of steel with load. We can see here axis. This is the load beam. This is the girder rope. This is the working load. This is the cracking load. This is the ultimate load. And strain in steel, we can see effective strain and initial strain and ultimate strain. This is the unbonded. This is the bonded, unbonded. So bonded would give the maximum stress in more stress than unbonded. Okay, you can see here the change of cable length over the unbonded. This is the math example as we've been seen here. Okay, let's see the a post tension sample beam is given. Beam is 40 feet and shown in figure. It carries the superimposed load 750, and it is into onward is initial prestress is given in and reducing error. And after the reducing all the assumption, no bending of beam, the parabolic cable is given at the square inch square, and is given compute the stress in steel mid span, assuming this grouting and steel unbonded early slip and span. All the data is given here. Okay, moment of mid span due to dead load and live load. We can see dead and live. We can see 30 into W 30 into 75, as we've been know this is the superimposed 75, and the onward, which is 30, and found this value. Moment at the midspan due to prestress as 2.5 to 200 into 5 is inches, and it will invert it to the feet, and found this value. 2.5 is as we've been found is given in question, so there is no problem at all. This is the area 2.5, and 120 this is the reducing initial prestress 120, and 5 is inch square, and it will converted to the feet, and founding this value. Net moment of mid span and deducting this value, and 585. Okay, let's see here the concrete at level of steel due to bending and using I gross concrete section is MY by I, and found 37 psi. Steel in steel thus increase, and using this formula, and found here, and result of steel, and found this way. And solution 2, we can see here, if the cable is unbonded and free sleeve, the average strain of must be obtained by the whole length of the cable given formula is given here, and using y naught and m naught of this mid span as is given here. So you can see here the example parabolic y diagram and parabolic movement diagram, parabolic elevation, and this is the mid span diagram. And express y and f's we have been founding this formula from this formula and putting here. So which 8 by 5 is the stress mid span, this is the 5 by 8, and bonded beam is 5 by 15, sorry it will be 8 by 15, and mid span 8 by 15, which is 11 into 220, which is 118 psi. The resultant stress is still this value and this value, and founding this value, and through this the entire table. In calculation, the gross concrete section is used, and the effect of increase the steel and concrete also neglected. But the error of second order, since the change of steel is relatively small and exact computer seldom require to accurate design of the problem. Okay. These are the index. So now we can see the cracking moment, ultimate moment. So where is the cracking moment? This is the ultimate moment, unboarded. Moment curvature. Okay, these are the cracking moment. We can see here the flexural behavioral and ultimate strength of the transformation, MCR cracking moment due to we can see and tension, the surface load, and F are the modulus of rupture. We can see the F was tension of bonded beam with the transformation of prestress F1 is given here, the being the roughly pickup and the mid span point is compute the critical fiber stress. Check the cracking, FCR is given, FC is given. So peak is upward, we've been seeing this is the pickup upward, FTR is given, F prime C is given, FCR the formula is given here, and found 3.62 equal to the area is given, and eccentricity d by 2 and 175. 175 is the location of the tendon, and I will point, and salto of the unit and W, which is unit and cross section we can found W, and what will be moment WL square by 2, as it is seem like cantilever, and found this value. Now FCR stress equal to F minus A plus minus F this value, and putting all this value, and founding at bottom minus 23, and for at top, and it will be 6.48. So F critical we have been found 3.6. So 6.8 is greater than 3.6. So the member will be cracked. Why we will compare with top? Because concrete compression zone is top. That's why we will compare it at the top. These are the compare with top. Okay. So cracking moment as ended. Now we'll see the ultimate bonded moment. Okay, let's see the ultimate bonding moment. Okay, these are the ultimate bonding moment. Before going to here, I'm just here. The exact analysis for the beam ultimate strength of prestressed concrete in section is under the flexural is complicated theoretical problem, because of the both steel and concrete are generally stressed beyond their elastic range. The purpose of the practical design there on accurate of 5% or 10% is considered the sufficient relative to some simple prestress produce can be developed. So you can see BW is here. There is the hands flange height. There is the web P. So if A is greater than H, then it will be rectangular beam. If A is greater than H, then it will be T beam. So you can see there is the B by 2, and this is the stress block A, and this is the D, and this is the T equal to SFS. M equal to force into perpendicular distance A into A divided by 2, which is A as FYD minus A by 2. As you know, this is the also the same below. For the ultimate moment, ultimate, which multiply the strength reduction factor M nominal into strength moment, and nominal we have been found here as FYD minus A by 2. So as FYD minus A for RC, for free stress FPS PS, and FPS we can use 1 minus 0.85 rho FU into this value. Okay, so rho we know the S into PD, another for free stress rho P, just giving the value of P. So WP we know the W rho divided by appearance in FPS, it is less than 0.3%, which is a balance condition. WP is a reinforcement of initial context. So there is some rho problem. We can find out the rho is BT 0.853 from this year. So when rho is greater than rho max, then under reinforcement, rho is greater than 0.5 with the over reinforcement. Rho max 50% to 80%. It is designed to the in practical field. There is a ultimate bonded moment tension. We can see here the N I shape beam is prestressed with as is given below. The prestress is still with the effective stress is given here. The seizures of the stand is which is separate. The prestress is 1/5 above the bottom of the beam, and shown is the figure given below. This is the figure along with the shown of the concrete cross section material properties is given. This the find the ultimate resisting moment of the section design following ACI code. Okay, so you can see these are the section. So given these are the value FPS and FPS. Now we can calculate rho. We know the S rho equal to A into S into BD, and finding this value. And stress, how will calculate stress ultimate into 1 minus 159 rho P into rho PU into rho efficiency, and putting the finding which is 1687, and which is the compression block, which is 17 millimeter, which is less than ACF. So this is the rectangular beam as 175 is given here. The total flange thickness. So this is the rectangular beam. So it will be analyzed as a rectangular beam. So now we'll calculate ultimate resisting moment using this formula and finding this value. Okay, so you can see here the diagram is given here. So if we see here, this is the flange thickness, this is the block, and this is the width of P minus 2 divided by 2 and D minus A by 2, and this is the compression load, this is the tension load. So A equal to A is still minus F is stress. So F flange equal to 0.85 flange P minus B ACF minus FPS. Ultimate equal to nominal into phi, as we've been used the web M equal to nominal web and nominal flange. So you can see that this is the web and this is the flange below. Okay, so let's see, this is the same thing, the ultimate moment and the ultimate resisting moment. The same I-shaped prestressed concrete beam is example 5.4, but the steel is the increase FPS which is 2356, and effective they still remain the same 1100 ampere. The seizures of stunt is 1/5 above the condition of the beam. Figure is shown below along the shape of the condition. The material properties of the given there, FPS is given, and find out the ultimate resting moment for the section design is ACI code. So all the data are as given as usual. So the steel is increase, which is 2350, and now rho equal to as equal to BD the same, and steel stress we know this formula and found, and the steel block we've been used the compression block and found here. So as we know, the compression block is greater than found 203, which is greater than flange thickness, which flange thickness is 175. This is the 175, the flange thickness, but we have been found the compression black is greater than 2 feet. So the beam will be analyzed as a T beam. So A is equal to as usually using this formula and finding here, and P is equal to found 9 and 4. After finding one data, then we can calculate the ultimate resisting moment, which is the m nominal into m ultimate, and m nominal will be oil plus flange. So we can using this data here and found 2.43. But we have been found in the previous lead, these are the 2.38, 10 to the power minus 10 to the power 3, and previously we have been found 1.8. Okay. Okay, so these are the indent. Now we can see the moment curvature analysis for bonded beam. Okay, moment curvature. Before going to the moment curvature, the following assumptions are made to connect it with the moment curvature analysis. So we can see here first, the change the strain in the steel and concrete after the bonding are assumed to be the same, which is steel strain of steel equal to strain of concrete, and then the initial strain from the effective prestress in the tendon shown no moment from the applied load act on the section and illustrated by the figure as the level of steel and the concrete compressive strain, which is given CC, and exists to which the tendon has been tensile strain, and which correspond to the stress is given, and which the initially effective. We've been see this is the strain in concrete. This is the strain of in the bottom, and the stress strain properties of the material are known to assume for the use of analysis. This is the stress strain, and strain are assumed to be distributed linearly over the depth of the beam in shown figure. The tension and compression force acting on the cross section and must be equilibrium for the beam, which has only flexural without any applied axial load. Okay. So let's see another example. Using the moment curvature analysis. So all the data is given here: PS, FSC, which is stress. This is the steel, and this is the modulus of elasticity of steel, modulus of elasticity of concrete approximate, and beta is given here. And we know the force equal to stress into area, or area into stress, and found this is the force and area, that the total section 1, 2, 3, and putting all this free and finding here E equal to D divided by 2 into 1 on 5. How will get 1 on 5? 1 on 5, this is the tendon location, the 1 on 5. That's why we are putting the 1 on 5 for calculating the eccentricity. And I, what will be I, and the total we have been taking the rectangle and detecting the two hollow side and finding I, and strain in steel plus compression zone plus compression tensile zone, and putting this formula and finding this 0.003, 0.008, 0.003, and this formula. And these are the we can see these are the equation 1, and we know the equal to beta into C, and C equal to A divided by beta 1. These are the equation 2. So we know the assume value. We have to assume at first we have been assume 175 as the flange. You can see the flange thickness, and it will be consequently we will assume again and again and again. See how we calculate C equal to A divided by B. Beta 1 beta is given 0.70 as per I know. These are the beta. The value is given 0.7, and found this value, and consequently all the data will found. I will calculate stress PS, strain PS, and these are the value. These are the equation, and 785 is the effective depth, 785. This is the 785, and C divided by C, and now we know that this value are the C, and finding this value, I will calculate the tension force, which is PS divided by 100, as taking the kilonewton, that's why divided by 100. Otherwise, tension force equal to stress into area, and finding this value. C, I will calculate the C, 0.85 F times C into AB. AB is given here, A is founding here, 175, and B is given for 460, which is this is the B, 460. So there is no problem at all. So we will find it. I will calculate C minus T. This is the C, this is the T, and we found the negative value. So C is much greater than T. So take the higher value of yeah, that's why we're taking the higher value. At first we've been taking the 175, and consequently we found here. So we've been seeing the C minus T is positive, so C is greater than, much greater than C, so T is smaller than, take the smaller value of here. So we are taking the smaller value of here and finding this value. So the same case, so we have to take the smaller value of here. So we can take the smaller value and smaller value, smaller value and smaller value. Consequently, we have been found the T value is 0. So we can see the our A value, we have been assume the A value is 193. So these are the answer. Okay, so these are the index. So now we'll see the composite section. These are the last. This is the last topic. So composite section we've been seen here. This is the precast. This is the cast in place. That's why we are called in composite section. In the bridge design, this is the girder in precast, and this is the deck slab of the bridge will be cast in place. That's why the precast. So we can see A plus WG, which is initial force plus weight of girder, and force plus F plus G, which is after the lossing value of F plus weight of girder, F plus GS into S. This is the plus slab weight. F plus GS WS into WS slab weight plus live load weight. These are the composite action, or total the composite action. Okay, let's see. Let's see the example. The mid span of the section composite beam is shown below. This is the composite beam is given below. The precast system is given 300 by 920, and deep is post tension is initial force is given 2850 kilonewton. The effective is free stress after the loss is taken as 2150 kilonewton. Moment due to the weight of the total precast section is 2700 kilonewton meter at the mid section. After it is erected in place, the top slab of 150 by 920 and weight of the precast in place producing a moment is given here 135. And after the slab concrete has hardened, the composite section is carried to the maximum live load is given 75 kilonewton meter, and compute the stress in section in various stages, and APS equal to 2400 mm square, APU is 1650 MPa, and FMC is 34 MPa. Estimate the ultimate moment. Okay, so these are all the data we've been seeing here. This is the 330, this is the 20, and all data is given. The initial force is given here. The after the loss is given here. Mg is given here. Ms is given here. M live load is given here. FPS is given here. FPS steel is given here. Stress, free stress is given here. F prime C is given here. Now we will calculate the E equal to D divided by 2 into 200. 200, how we will calculate 200? This is the tendon location from bottom. This is the 200 and found this value. Y equal to D divided by 2, as we know that D value is given as the 920. This is the girder that divided by 2, and found I equal to the moment of inertia is found. Okay, so stage 2, these are the stage 2 when when precast, which is called F0 and mg, and after the putting this value, which is it will be always negative value as the pre-stress. That's why f it will be minus f divided by a, and plus minus f not into f not into e into y divided by I, and minus girder into I into I, and putting all these value and founding 0.04 ampere, which is close to 0 is at top, and minus 70.46 at bottom. For stage 2, for final, as we know, this is the final f we will use, and this f will be also final. But remember that when stage 2, when it is precast, this f is the initial, this f also initial. But on the other hand, we have been seen here, this is the final f we have been used here. So stress we have been found is close to 0 at top, minus 0.97, but on the other hand we have been found 14.61 at the bottom. Stage 3, f into mg into a, so we can use all this data, minus f into a, minus f into I into, we've been seen for slab as 137 as given here for slab composite, where ms, this is the 135, so there is no problem at all, given on the data is given 135 is the producing moment 135, the plus in place producing 135. Okay, so 135 we've been using here, and at top it is given minus 4.5, at bottom we've been found 11.3. so this is the fourth stage, which is force, girder, slab and live load. All the data is given here, but remember y equal to y bar, I equal to moment of inertia, and finding this value, and at the top we've been found minus 4.6, and the bottom at the top 8.63 and bottom 4.61. But when we calculate the y bar, we've been found this value, and 663, and moment of inertia is from this value. Okay, we can see here the graph is given here. If we calculate the graph here and finding here ultimate moment capacity, if we calculate here this value, so d prime is also founding here, so we know the rho equal to s into bd, and fps equal to, we can use this formula and found this value, and tension we've been finding this value. So after finding the tension, now we'll calculate the stress, force into area, and finding, if we calculate the area into force into stress, and finding this area. Now area we know, width into depth. Depth is known, the we can calculate this depth as the a, and width area we've been found is here, and width we know 920 in the question. These are the width, and finding this value of air. This is the value of air, which is compression drop 137. Now moment, we can moment of d prime into air, we've been finding here the nominal moment t into moment term, and finding this value. The ultimate moment will be the factor 0.90 will be used, and found this value. These are the answer. And I think in the composite section also completed. So these are the very big lecture. I'm just saying, summarize again. This is the analysis section of flexure, that means beam, and I have been introducing the sign conversion, positive negative, compression for minus, and tension for plus, and stress in concrete due to prestress load. For prestress load we have been calculating this type of math, and for the stress in concrete due to load, and this type of math we have been used, and concrete is still this type of math, and we will calculating tacking moment, and then ultimate moment, bonded tendon, and moment curvature analysis, bonding beam. It has a bonding tendon and composite section. Thank you everyone. If you have any question, then let me know.